acceleration. So we're going to integrate acceleration with respect to time. Now, for this one here, we're just going to assume that acceleration is constant. I should have said that before. So we're using constant acceleration. So we're accelerating acceleration with respect to time. If you integrate acceleration, then it's just going to be the two things you remember for integration. One, you raise the power. And two, divide by the new power. So if we've got a t to the power 0 dt, are you happy with why I've written t to the power 0 there? Because that's just a constant, and we're integrating it with respect to time. So because t to the power 0 is equal to 1, it's effectively a times t to the power 0 dt. If you integrate a constant, you're effectively raising the power t to the 0. You're putting it up one power, so we've got a times t to the power 1. T to the power 1 is just t. Dividing it by the new power is now 1, divided by 1, plus that constant. Okay, so all we're doing is integrating constant acceleration with respect to time. And so if you integrate a constant with respect to t, it's just going to be a times t. That is, because we've integrated velocity, that's now going to give us velocity. So v is equal to at plus a constant. Because at t equals 0, v is equal to u. We've got v equals u plus at. Okay, that I hope is a clearer description of it. Thanks, Donald. The first one wasn't particularly clear, but I'm perfectly willing to answer questions on that one now.
How did you get that integral of all that jazz on the left side is v?
Because that's what we were saying before, that acceleration is dv by dt. So the acceleration there, if you integrate acceleration, you'll get velocity. Yeah. So that's our first equation of motion. That's taken half the board. We've still got 2 to go. The next one follows a similar process because we know that v is equal to ds by dt. Can we get the second one by a similar process? So we're saying that velocity is the differential of displacement with respect to time is equal to at plus u. I'm going to give you a minute now to think what you could do with that. Would it work? Could we go through a similar process to get to our second equation of motion? So we're going to take this function here, which is v equals u plus at, just written a slightly different way here, and going to then integrate this one. So because displacement is the integral of ds by dt with respect to time, so if we integrate that, we should be getting s. So it's the integral of at plus u with respect to time. And you've all, by yourself, said, well, at, raise the power of t, we get at squared. Divide by that new power, that's dividing by 2, plus u. It's just a constant in that line, so integrating with respect to time, you're increasing the power of t to the power 1, dividing by 1, so it's this left is ut. And you were all very happy with that, but you had, to a person, forgotten one little thing. Is there a constant? So at time t equals 0, what's s equal to? Yeah, we generally start things at a 0 point. We say that when something's starting to move, when the stopwatch starts, we assume that we're measuring the distance from that point. So although you've got a constant, s is equal to 0, so we've got that s equals half at squared plus ut, which is our second equation of motion. In between there and there, we somehow need to get v squared equals u squared plus 2as. And the procedure for that is very similar to the procedure that you used last year, because you've got two equations, one with vu, a, and t. This one's got s, u, t, and a in it. What you want is v squared equals u squared plus 2as. We want to get rid of the t in that one there. So can we get rid of t? The easiest way is to say, well, from this equation here, t is equal to v minus u over a. Replace that t into this equation here and here, and then it usually takes 6th-year students under 5 minutes to do all the algebra to get from that substitution by doing things like expanding brackets, collecting terms, dividing by what's its well, all that sort of shenanigans to get to that one there. Maybe do it in the back of your notes, Dora, so it doesn't mess up your real notes unless you're feeling really confident. That's really going to be the 3 steps that I'm going to go through. Multiplying through by 2a, expanding out the brackets, and then collecting terms. So see if you can follow that to end up with the final line. Let's just take it through. So we've got, putting in v minus u over a wherever there's a t, we've got s equals half of a times v minus u over a all squared plus u times v minus u divided by a there. First thing I did mention to do is to multiply through, get everything on top. The two things that are on the bottom at the moment are 2 and a. So I've got 2a times s equals a squared, v minus u squared on top, a squared on the bottom. That cancels. Plus u times a, because there's only one a on the bottom. Oh, no, sorry. There's one a on the bottom, one a on the top there. So it's 2u times v minus u. So that's all I've done there, multiplied through by 2 times a. So this is looking promising. I've got 2as on that side. Over here, v minus u squared, v squared, minus 2uv, plus u squared, plus, expanding this bracket out, 2uv, minus 2u squared. I've got, the nice bit is that the 2uv minus plus 2uv cancels. I've got v squared there. I've got a plus u squared. I've got a minus u squared. So we've got v squared minus u squared equals 2as. Rearrange that, and you get v squared equals u squared plus 2as by taking the minus u squared over on the other side. That is your third equation of motion. Now, some of you are thinking, well, big deal. We've used differential calculus and got exactly the same point that we got with using velocity time graphs last year for constant acceleration, because these 3 equations of motion still only apply for constant acceleration. The good thing is, and this is the thing we'll be going on to next time, is how do we then treat motions with varying acceleration? You can do the same thing. You might have an acceleration which isn't constant. You might have an acceleration that depends on time, but again, you can integrate it. You might have then that can be integrated to give you velocity and then to give you displacement. Even though the acceleration depends on the time, that's what we're going to go on to next time.